Hello and welcome once again for another Physics 1 video. Today we will be discussing velocity, position, things like this. So an electron is moving along the x-axis and has a position given by x equal to 16t times e to the minus t meters, where t is in seconds. How far is the electron from the origin when it momentarily stops? Well, we're going to look at, of course, that we have the position, and we're going to notice that the word momentarily stops. So that means that the velocity must be 0 meters per second. And the velocity is just the derivative, or instantaneous velocity is just the derivative of the position with respect to time. So we're going to be using the position here. So we can write this out as dx dt. So v is equal to dx dt. Now if I actually take this derivative, I'm going to need to use the product rule, because notice that I have a t times e to the minus t. So I have two functions of t multiplying each other. Now the 16 is just a constant. So the constant obviously gets multiplied back in because of the fact that the derivative is just a limit, so it follows those beautiful limit rules. So I'm going to take the derivative with respect to t of that position, so dx dt. Now I need to write it out in terms of the product rule. So notice that the 16t part there, the t part is going to get, we're going to take the derivative of that and multiply it times the e to the minus t, because that's the way the product rule works. And then we have to add it to the taking the derivative of the e to the minus t part and multiplying by 16t. Right, so the 16 is going to end up in both pieces in this product rule. So let's actually take that derivative. So the t, when you take the derivative of t with respect to t, well, that's just 1. Okay, so that's going to be 16 times e to the minus t. For the second part, when I add this, now using the product rule again, when I add this to the other part, I have to take the derivative of e to the minus t. And technically we need the chain rule here, but it's simple enough that it just, you take the negative in front of the t and pull it down, and you just get back e to the minus t. So doing this, I can see that I have 16 e to the minus t minus, because that minus sign is going to multiply everything, minus 16t e to the minus t. So I'm going to write that out. But there's something else that we should notice. I need to get rid of that and make this a minus here. I was doing a plus there. The next thing that we should notice is that we can pull out a 16 e to the minus t factor, which is what I'm going to do. So I'm going to have 16 times e to the minus t times 1 minus t. Now we're looking for when this electron momentarily stops. So I want this velocity to be equal to 0. Notice that after I've taken the derivative, now I have a function of the velocity. So I'm going to set this equal to 0. And hopefully we shall see that when I do that, this is very easy to solve, because e to the minus t can never be 0, except for if you let t go to infinity, which is obviously not something that we consider. So the only term that can be, because we're multiplying out these terms, 16 times e to the minus t, neither one of those terms can ever be 0. But if I multiply by 0, everything goes to 0. And the last part is 1 minus t. So if I set 1 minus t equal to 0, then the velocity here will be equal to 0. And that just means that t is equal to 1, because obviously 1 minus 1 is 0. So we get t is equal to 1 second. But that's not the end of the story, because we need to see the position when t was when t is equal to 1, which is when the particle momentarily stops. So let's write out the position again, which was 16t e to the minus t. And I'm just going to substitute in 1 for t here. So that's going to give me 16 times 1. X is going to be equal to 16 times 1 times e to the minus 1 meters. And e to the minus 1 is just 1 over e. So I can give the exact answer as being 16 divided by e meters. Now you could obviously plug this into a calculator if you wanted to get an exact solution, but that's what our solution is going to be to this problem, to get an approximate solution, I mean. So that's all that I have for this video. I hope you enjoyed the content, and I hope to see you again next time.